All right, so we're starting a new topic today, and the topic is a direct result. The existence of this idea as an important thing in operating systems is a direct result of what we were talking about before. Okay, before we had been saying, well, look, processes need to share resources. Okay, we have situations where multiple processes need exclusive access to multiple resources because the order that they access those things, right, is important, okay? And so we identified the notion of critical sections, we talked about mutual exclusion, and we ended our discussion of synchronization with semaphores, okay? So this notion of semaphores, which is, okay, so this is all review, obviously. We haven't been tested on this, but this was our last new material before the test. So semaphores give us the idea of locking resources, okay? And what that means is that we are going to associate for a period of time a resource with a specific process, okay? And when that process is done with that resource, it can release the resource. But until such time, no other processes can have access to that resource. Okay. Now, in a perfect world, that is not a problem. Okay. But consider these two facts. One, processes regularly need multiple resources simultaneously. Okay? To complete what they're doing. Fact number two, there are often shortages of resources. Not all processes can have all the resources all the time. They can't have all the resources they need all the time because there are not enough. There are not enough resources. Fact number three, resources have to be acquired one at a time. Okay? Because the act of acquiring a resource means that it is an operation, and if you're going to execute that operation, it means that you need to be the running process. Okay? So with these three facts in mind, that opens up the possibility of today's new topic, which is deadlocks. Okay? Now, I briefly introduced deadlocks in a sentence or two in a previous lecture, and you may recall a simple example. We talked about deadlocks. I talked about how it's kind of like gridlock, right? When you're driving a car and you get in a gridlock situation. Effectively, it means that no process can go, or at least some number of processes cannot go, because they are all circularly waiting on each other to finish. Okay? Simplest kind of deadlock is a two-process, two-resource example. Okay? And all we need, right? Well, we're going to talk about 4 requirements for developing a deadlock situation. But all those requirements can happen if you have 2 or more processes and 2 or more resources being shared amongst those processes. Okay? If you're the only process and you're the only guy who needs that resource, or you're the only process at all, then you can never have a deadlock. But then again, you can never do synchronization either. It doesn't matter if you're the only process. Okay? So what does this look like? Here's an example. Let's say 2 processes want to play an audio file. Okay, same audio file, 2 different processes, both want to play it. All right, so we're looking at two processes. Call this process 1. We'll call this process 2. And here is the audio file. And in order to play the audio file, you also have to have access to the sound card. Okay? Process 1 is running. Process 1 is gonna do this. It's gonna acquire, well, it's gonna request rather. It's going to request the file, and it's going to request the sound card. Okay? And then it's going to run its algorithm. Okay? And then it's going to release the file and release the sound card. Okay? And process 2 is going to do the same thing. Okay? They're both going to request the file. They're both going to request the sound card, and then their algorithm is going to finish. Okay, so if process 1 requests the file, let's say it gets the file as a result of that request. Okay, process 2 asks for the file and has to block. Okay, so let's say right here there's a context switch. Okay, process 2 asks for the file and has to block. Then process 1 can continue, and we get process 1 able to finish its algorithm. Process 2 has to block. Then these are released. Okay, then process 2 is able to ask for them both in turn. Release, finish. This is not a deadlock. Okay, but look how simple it is to turn this into a deadlock. Now I'm going to reverse the requests for process 2. Okay? And then request the file. Right, in that order. And then of course they do process 2 does its algorithm, and then it releases those two. Okay? So let's try this again. Do we have a problem now? Process 1 goes first. It happens that after the request and they receive the file, they get context switched off, and then process 2 runs. Okay? So the file is requested and received by process 1. Then process 2 runs, and it asks for the sound card. Okay? Now either it gets context switched right there, or it runs its next command because it's going to try and request that file, but it can't have that file, okay? Because P1 has it, right? Until P1 releases it, we know that P2 is going to be blocked. Okay, so we'll draw a request toward the file, toward the resource. Okay, this is asking for the resource. This is having received the resource. The direction of the arrow matters. Okay? Likewise, when P1 gets back goes from ready to running, he's going to request this. P2 is going to block waiting on P1, and P1 is going to block waiting on P2. And since they're both blocked waiting on each other, okay, and neither one of them can run, right? This is a deadlock situation. And it's a deadlock situation that semaphores in and of themselves not only cannot prevent, but actually kind of allowed. Okay? Because we needed to request resources and receive resources before we continued. Okay? Does that make sense? All right. This is, as I said, the simplest kind of deadlock to kind of imagine. They get much more complicated than that, right? Because you can imagine, what if we've got hundreds of processes and hundreds of resources? Many of those processes may not ever be deadlocked, but some number of them, in some complicated way, are waiting on the rest, or some other, which is waiting on another, which is waiting on another, which is waiting on another, which might be waiting back on me, okay, then the ways that those can come about is very complicated, okay, and also very numerous, right? So deadlocks happen all the time, and they always lead to a system that can't finish, right? The programs can't finish what they were doing. Right? They can't successfully terminate. And so we need some way to deal with them. And there's no easy way, okay, to make sure that as a programmer, I'm not programming my code in such a way that it won't interact with some other programmer's code and eventually cause a deadlock. Okay? You might say, well, let's request all files first and then all hardware. Right? It's not as simple as that. Oftentimes you don't know what your program is going to request or when it's going to do it, and you certainly don't know when it's going to run. Okay? So we need some operating system techniques. The operating system needs to be aware of some techniques for how to deal with deadlocks. All right, any questions so far? You guys are real quiet. What kind of things are resources? Devices, records, files, any memory, okay? Any drivers, right? Other programs.
When I use some SQL, I also play with something like deadlock, so it's the same.
Yeah, same idea. If I need to have, because when you're doing database stuff, you need to do atomic operations, right? Operations that not only calculate, not only read, but calculate and write, and they do it all or none, right? So in order to do that, you actually have to lock your resource. And in this case, the resource would be a table, okay? So if I lock this table and another process locks another table, and I need that table and they need this one, we've still got the same problem, it's still a deadlock. Okay, so in that case, the operating system needs to be aware. It generalizes to, we've got limited resources, multiple processes, all asking for multiple resources in multiple different orders. So how do we break deadlocks? Yeah, it's the same idea. Yeah. Okay, so let's talk for just a second about the 4 conditions that are required for us to enter into a deadlock situation. Okay? The first is mutual exclusion. Second, hold and wait. Okay. Third, no preemption. And fourth, circular waiting. Okay. We talked about what mutual exclusion means. Somebody give me a brief definition of what that means. What does it mean when something is mutually exclusive, when 2 things are mutually exclusive?
The relationship is 1-1.
Okay. All right. Yeah. Effectively, that means that you can't have this with this. Okay. And the mutually exclusive relationship that we're talking about here is you can't have 2 processes accessing the same resources at the same time. Okay. So if our resources are mutually exclusive, it means that only one, there might be multiple copies of that resource, and in which case we're talking about only one copy of the resource. But only each individual resource is only allotable to one process at a time. Okay? that was a big thing from synchronization, okay, from chapter 4, right? Because we needed that. We decided we needed that in order to make sure, for one thing, for example, that that processes did not enter into their critical sections simultaneously. Okay, we can lock out access to resources in that fashion. Okay, so that's mutual exclusion. Hold and wait is when a process currently holding a resource can request new resources. Okay? We do that because we don't believe, we know, let's go back to our facts. We know that processes regularly need multiple resources simultaneously, and we also believe that there are a shortage of resources. Okay? So if you're going to get the resources that you need, you're going to have to request a resource and then hold that resource until you get the other resources that you need. Okay? And if you're blocked on waiting for a resource, just because you're blocked doesn't mean you release all the resources you have. Okay? If you release all the resources you have, then you run into a starvation possibility. Okay? If all processes have to have all their resources at once, otherwise they release whatever resources they held if they're going to go into a blocked state, then you got a starvation. You guys, I think on Tuesday before the exam of last week, I released a video where I talked about the dining philosopher problem. Okay, and you'll recall that each philosopher has a plate of food in front of them. Okay, and there is a utensil on the left-hand side and a utensil on the right-hand side. Okay, and philosophers do only two things. What's that? What do philosophers do? There's only two things in this toy example. They got food in front of them, so what do you think one of it is? Eat. And what's the other thing they do? They do what? Think. Okay, let's say they think. Philosophers don't like to talk to each other. They don't even like each other. Okay? They only do two things. They think and they eat. Okay? If they think, they're not eating. When they get hungry, they try to eat. Okay? In order to eat your plate of spaghetti, let's say, you need both the left hand utensil and the right hand utensil in order to eat. Okay? The problem is that my left hand utensil is the guy on my left's right hand utensil. There's only one utensil between us. Okay? And only one utensil between the guy on my right as well. So we're sharing, this guy and me are sharing this utensil, this guy and me are sharing this utensil. So how can I write an algorithm that always makes sure that no one starves? Okay? And in this case, we mean literally starve, just can't eat, right? One approach would be, if you can pick up, and it's arbitrary, either your left or right first, doesn't matter. But if you can pick up your left utensil, you pick it up, okay? And if you can pick up your right utensil, you pick it up, and now you're ready to eat. But if you can't pick up your right utensil, what do you do with your left utensil? One option is to release it, okay? And that seems like a good solution until you imagine sort of what could happen. Okay? All of us could pick up our left utensil. Okay? So I pick up my left utensil, we go around this table. Guy to my left picks up his left utensil, pick up, right? This one's gone because this guy's got it, right? I look over, and I don't have a right utensil. So now I put down my, and I'm ready to put it down, but I get blocked, okay? And then this guy looks over and he's ready to put it down because I've still got his right utensil and he's ready to put it down, but he gets blocked. And that happens all the way around the table. So our next move, all of us, is to put all the utensils down, okay? Then we pick all our utensils up and get blocked in the same order. So effectively, synchronously, we're all putting down our left utensil, picking up our left utensil, putting down our left utensil, like the whole table, okay? So that's not a solution that is going to work, okay? And in general, not only is that not a solution that's going to work, it's also going to really slow down all your processes if they have to be able to find all the resources they need before they're able to hold any resources at all, okay? So far, we like mutual exclusion, we like hold and wait. Preemption is the idea that one process can force another process to relinquish the resource so that they can have it, okay? What's the problem with that? They will interrupt another process, absolutely. Yeah, if they force it to release. Also, that's not the job of processes, right? Processes should not even be aware in our design, our simple design, that other processes exist, okay? And that leads to a whole level of other sort of rollback problem, okay? You've got all these things, now you're being forced to release those things, okay? So now your instructions have to be backed up as if you never got them in the first place, okay? So there's a lot of overhead for doing preemption, okay? So we like to have no preemption. And the final thing is circular weighting. Everybody, we got to make sure that everybody is waiting on everybody else is a possibility, okay? Well, no points for guessing, but really number 4 is eventually where we're going to try and target, okay? We're eventually going to get to, yeah, let's look and see how we can address number 4. Can we identify and can we fix circular weighting? But before we do that, let's more generally describe a model for resource allocation. And I've already kind of shown it to you. It's very simple. This model is called the resource allocation graph. Okay? Resource allocation graph. Processes are circles. Squares or rectangles are resources. If there are multiple copies of a resource, then you've got a circle inside of this rectangle for each copy of the resource is a circle. Okay? If you have an arrow leaving a process and arriving at a rectangle, that is a resource request. If you have an arrow leaving a box or a resource and arriving at a process, that is a resource allocation. Okay? This is the process asking for a resource. This is the current state of the system where a resource has been allocated to a given process. Okay? And if you have like multiple processes or multiple resources, you'll sometimes see an arrow coming into a specific resource and a specific resource being sent out to a specific process. Okay. Notice that, yeah, we tend to simplify things usually with resource allocation by just thinking of resources as being whole units. And we can usually get away with that because adding copies of the resource doesn't really solve the problem. You can add copies of the resource and I'll just have more processes requesting those resources, right? And so Sometimes it's useful. Sometimes it's useful to think about the individual copies, though. So that's supported in the resource allocation graph. I have, I think, a example for you. Yeah, that's just the simplest example, kind of like what we did before, right? Where process A is holding on to resource R. Process B is asking for resource S. Okay, it's requesting resource S. And this is process D requesting resource U, which is allocated to resource C, and process C requesting resource T, which is allocated to resource D. Okay, so this is, again, the simplest form of deadlock. Okay, process D cannot get process U because process C has it, and process C cannot get resource T because process D has it. Now, if you build your resource allocation graph following these rules, then it is no accident that deadlocks are represented by cycles. Okay? All the deadlocks that you can find, no matter how complicated your resource allocation graph is, will be represented by a closed cycle, okay, of processes and resources. Okay? So with this, let's talk about possible state transitions that can happen in the resource allocation graph. Transitions that affect the resource allocation. Siri. Allocation graph. Okay. There's only three of them. Only three things that processes can do that that will change the resource allocation graph. Do you want to take a stab at what they are? A couple of you are looking, so that's cheating. Do you want to take a stab at what those three things are? There are three things that a process can do with a resource. Okay, so what you are saying is what I would call resource allocation. Okay, I can be given a resource. Okay, and when I'm given a resource, then the arrow changes from the resource to the process. Okay? There's a couple of rules. There's a couple of rules involved with resource allocation. I'm only going to be allocated one resource at a time. In other words, one resource per, well, what's the first type of transition that can happen? Before I allocate or acquire a resource, before I'm allocated a resource or I acquire a resource, as a process, what do I have to do? Okay, so the first one here is request a resource. Okay, and what that looks like in the graph is when I draw a request like so. Okay, if I need to request a resource, then I draw a new arrow, and those arrows always go from processes to resources. If I'm going to be allocated a resource, then that means that an already existing arrow is going to flip directions, okay, in terms of my model, right? So it's going to now point from the resource to the process to indicate that allocation has taken place. The only time I can do this is if I'm not already blocked. Or more specifically, I can only request a resource if I am the running process. Okay? So I can have processes that ask for a resource, receive the resource, and ask for more resources, right? All in one time quanta. Or I can have a process that asks for a resource, has to wait on getting that resource, and therefore becomes blocked, at which point they cannot ask for more resources until they get the original resource they asked for. Okay, does that make sense? You cannot be waiting on a resource and still requesting new resources, because if you're waiting on a resource, you become blocked, and you cannot request more resources if you are blocked. You have to be running. Okay? And the other thing, should be somewhat obvious, is that there will never be a time where I request more resources from the system than exist in the system. Okay? Such a thing would be paramount to a programming error. Okay? You have written your code in such a way that it cannot run on this computer. Okay? Therefore, the operating system cannot save you. If you demand more resources than this computer can ever provide, right, then it's not the operating system's fault. So we're going to assume there's nothing to keep people from doing this, but their program will not work and the operating system doesn't care. Okay? So then we're going to make that simplifying assumption. All right, so we got first, request a resource. Second, get the resource or resource allocation. And what's the third thing? Release a resource. Okay? In general, you must be running. This is always true. I must be running to release a resource. Okay? It does not have to be that I release all my resources at once, but certainly when my program finishes, it will release all of its resources at once. But I have to be running in order to release a resource. And if I'm blocked, again, if I'm blocked waiting on a resource, then that means I'm not running, and therefore I cannot release a resource that I already have. Okay? And the foil to this one is that I cannot release more resources than I was allocated. And I'm going to stop using the word allocated. I like the word acquire. Question so far? Anything? Sounds very simple. Problem is that it's not. Because the simple versions of deadlock are simple, right? If you are limited to only a handful of processes and only a handful of resources, then it's fairly easy to check to see if there's a deadlock. But deadlocks can emerge in between two executions of synchronizing multiple processes. One will cause a deadlock and one will not, and it will not be necessarily easy to tell before you go into a deadlock, which one of those executions is going to cause the deadlock. Okay? Let me show you what I mean. So this is a good time for me to point out that some of this material is not in the Xi book. I'm pulling resources from other material, so this is not all going to be in your Xi book. And also, some of my explanations are going to be slightly different than those in the Xi book. You're still responsible for the explanations in the Xi book and the additional material in the Xi book as well. But just want to point that out. All right, so here's an example. We've got resource A, process A, process B, and process C. 3 processes and 3 resources. We know that A is going to request R, request S, release R, release S. And B is going to request S, request T, release S, release T. And C is going to request T, request R, request release T, release R. Here's the order. Well, the answer is on the screen already. But here's the first order that we go through. Now, honestly, ask yourself, if the answer was not already there, would you be able to tell by looking at that series of executions if this was going to lead to a deadlock? Well, if we run through the transitions, because effectively this is 6 transitions to this graph. A requests R, and then A receives R, right? There's a secret transition in between each of these. They get it if they can, okay? So A requests R, and R is given to it. B requests S, and S is given to it. C requests T, and T is given to C, okay? Then A requests S. That looks like that. A cannot have S. Why? It's already been allocated to B. Yep. So there's only one of them. A's got to wait. Now, B requests T, can't have it. And C requests R, can't have it. They are all blocked, okay? And they are all waiting on each other. Right? You can follow a cycle of these arrows, okay? Back to whatever point you start from, okay? Therefore, this is a deadlock series of requests and releases. We never got to any releases, in fact. Here's the same processes, same series of operations, different order. A requests R, gets it. C requests T. Notice, we're not breaking anything. C is going to request T first anyway, right? These programs are running in this order both times, okay? The only thing that changes is the order that the programs run on the processor, okay? And when they get interrupted. So C requests, got lost. C requests T and gets it. A requests S and gets it, okay? Because S has not been requested by anybody. C requests R and blocks, okay? All right, then A releases R, okay? And then C gets it, okay? Because it became available. A releases S, okay? C releases, then it doesn't matter in what order it happens, okay? Because all that's left is for C to release and B runs in its entirety. Okay, does that make sense? So in that permutation, there's no deadlock. Same programs, 3 different programs run the same order of instructions internally, and all that matters is the interleaving of those instructions. Okay, to lead to either a deadlock or a not deadlock. outcome. Okay? So the question then is, can we, in general, come up with techniques and solutions for surviving the possibility of deadlocks? And that means one of a couple of things. It either means that we are going to, one, ignore the problem and hope it'll go away. I would not call this an engineering solution, okay? But it's not something you probably want to do if your users expect the system to work all the time. But if you're in a constrained environment where the users are really not interacting with the computer or the programs that are running, it might be just as good to let them deadlock every once in a while, check to see if it looks like there's a deadlock. If there is, restart those programs. Okay, that's an option. It's not an option in the general case, but it's an option in limited cases. Okay, for interactive computers and interactive processes, this is not something we want to do. Okay, so what are the real engineering options then? 2, 3, and 4. Make sure I do them in the right order. Yeah. Detect a deadlock. Okay. Avoid deadlocks. Okay. And lastly, prevent deadlocks. And when we start talking about preventing deadlocks, we're discussing tackling one, at least, of the 4 requirements that lead to deadlocks. Okay? If you can make a program where at least one of those requirements, if you make a computer system where at least one of those requirements doesn't hold, then you can avoid deadlocks altogether. You can prevent deadlocks. Okay? That's the last thing we're going to look at. First, we're going to talk about how to detect a deadlock. And if you detect a deadlock, then you're also going to want to recover from a deadlock. We're going to focus today on this, and this is predicated on this. Okay? And it's its own sort of field of study. Okay? But we're going to focus just on the detection part for right now. Okay? How do I know if there's a deadlock? Okay? You can avoid deadlocks. How do I identify a deadlock, the possibility of a deadlock in the future, or the certainty of a deadlock if this request happens, okay? And if I can do that in real time, I can do it before the deadlock occurs, then maybe I can take steps to reorganize how the instructions are, in what order the instructions are being run, right? If the operating system is smart enough at identifying deadlocks, it can look ahead for each process request, determine if that request is going to cause a deadlock or might cause a deadlock. And if it might cause a deadlock, block it, okay, for a period of time. Or put it back in ready. Either one will be fine. Put it back in ready and just let another process run, okay? We're just going to avoid deadlocks altogether. So today we're probably going to look at number 2 and number 3 there. Detect a deadlock and avoid a deadlock. Now that's how far we got in Tuesday's class. Okay. All right, so first off, deadlock detection. Let's talk about let's talk about different states, different system states. There's the deadlocked state. Okay? Kind of have an idea of what that is. That is where, formally speaking, that is where there will always remain two or more blocked processes if, no matter how many, what kind, what order of transitions take place into the future. And that's a deadlocked state. Right? And remember, the transitions are request, get allocated or acquire, and release. Okay? I can't release something if I'm blocked. Right? So no matter what transitions, what possible transitions happen in the future, if there are two or more processes that are blocked, regardless of what transitions happen, then this is a deadlocked state. There's also this notion of a safe state. Okay? And in some way, they are inverses of each other. Okay? A safe state is one where no matter what transitions happen, we will never get to a deadlocked state. Okay? From the current state. What that means is not only that there's no deadlock in the current state, but that there cannot be a deadlock in the current state, no matter what transitions, what allowable transitions take place. Okay? So keep that in your back pocket for just a second. So, how do I detect a deadlock? Well, the static way to do it is by something called graph reduction. I'm thinking back, algorithms. How many of you guys have taken the algorithms class? I don't think they call it that here. What do they call it? Well, anyway, there's a kind of problem called a topological sort that uses graph reduction. So if anyone's heard of that, I can talk about it. But if you haven't heard about it, then I have no need introducing a new thing. You guys heard of that? Okay, don't worry about it then. Just know this is the same thing. Graph reduction is removing things that are not blocked. Okay, processes that are not blocked. So it's a two-step process. Select an unblocked process. Any unblocked process will do. I'll tell you why in just a second. Select an unblocked process. You've got a graph in front of you. So you select an unblocked process and you remove P, the process, remove that process. And when you remove that process, you also remove all of its acquisitions. Okay, the process is gone, and all the arrows pointing to the process are gone. Okay, so effectively, it's as if that process finished running. Okay, and it released all of its resources. And then, as a result of this, if any requests can now be filled, then do so. Okay? Repeat. All right. What are the two possible outcomes of repeating this? talk to me about it in terms of the graph that's going to be left. Yeah. You could end up with no processes. Yeah. And if you end up with no processes, then that means you do not have a deadlock in your computer in current state. Okay? Because there was some path, okay, where the process is finished, okay, and you found that path because you only chose unblocked processes. So there was some path where the process is finished and they were able to all able to finish. And if any path like that exists, then you do not have a deadlock currently. What's the other option? Obviously, the other option is that there will be a deadlock, but what will the graph look like? Tell me some characteristic of a deadlock graph. It has a cycle. Okay? If there is a cycle, then you will not be able to remove all the processes following this graph reduction. Okay? If there is not a cycle, you will be able to remove all the processes. If there is a cycle, there is a deadlock. Okay? That the graph the resource allocation graph is designed that way. Okay? By definition, if there's a cycle after a graph reduction, then you have a deadlock in your system. Okay? So this is static deadlock detection through graph reduction. You can start at any resource allocation graph and determine if there is currently a graph a deadlock through graph reduction. Okay? There's a couple of related theorems. Hang on, I know you can't see. That are important. Okay? And this nomenclature, theorem 1 and theorem 2, is out of your book. It says, theorem 1, a state S is a deadlock state if and only if the resource graph of S is not completely reducible. Okay? Because of what cycles mean in the graph. Okay? In theorem 2, all reduction sequences of a given resource allocation graph lead to the same final graph. All reduction sequences lead to the same final graph. Now, I don't provide a proof here, but notice that the fact that that theorem is true is what makes this graph reduction so powerful, because it does not matter which unblocked process I pick first. If I unblock a process, or if I find an unblocked process and I finish that process, okay, and then I reallocate its resources, as long as I can keep finding unblocked processes to do that for, then that is paramount to some ordering, and any ordering is the same, leads to the same final graph, okay? And so it doesn't matter which order I pick those processes in. Okay? Still in the domain of deadlock detection, rather, let's talk about continuous deadlock detection. There's a couple of facts that we need to make ourselves aware of. If the current state is not deadlocked, okay, then the next state S, the next state S prime, can be deadlocked only if one, the operation that caused the transition was a request for a resource. Okay? Does that make sense? The graph is not deadlocked. What are the three possible things that can happen? Acquire, okay, which means that it's available. Release, which just makes our lives happier. The only thing that can cause a deadlock, a new deadlock, is a request. Okay? And two, it must be that the requesting process is now involved in the deadlock. Okay? Because a requesting process cannot cause a deadlock without being blocked, without being the trigger to that deadlock. Okay, does that make sense? So effectively what that means is I can have an algorithm. Let's look at it. This suggests an algorithm. If the current operation is a request and the requesting process becomes blocked, then if we execute the graph reduction algorithm, okay, if the recent request, now let me restate this. If the recent request was if the recent transition was a request, okay, then it's only possible to have a deadlock if the requesting process is involved. So it's sufficient to do graph reduce only until the most recent process P is removed. Okay? Then we can stop. Because if P, the requesting process, can be removed, then there can be no other deadlock that evolved, okay, out of the prior state, which we knew to be deadlock free. Okay? So with this, it's now clear, or should be clear, that it's not necessary to completely reduce a graph any more than one time. Okay? Then we only need to reduce graphs upon requests, and even then, we only need to reduce the graph until some arbitrary point where the requesting process is shown to have been removed, or that won't happen, in which case we'll find a deadlock. Okay? All right, so questions? Let's talk about deadlock avoidance. Okay. We can avoid deadlocks if all processes report on their maximum claim. Okay? In other words, we need every process to tell us up front the maximum number of each resources that they are ever going to request. Okay? They tell us up front, I'm going to need at some point a maximum of 7 integer addresses. Okay? Or I'm going to need at some point a maximum of the of one spot in the print spool. Okay? Whatever the resource is, they tell us their maximum claim on it. Incidentally, this approach is, again, thanks to Dijkstra, who also was in charge of inventing, or who invented, the semaphore. And this is also the same Dijkstra who's now trying to tackle deadlocks. Created a problem, tried to fix it. Okay? All right, so how does that help us to have a maximum claim? What does that mean? It means that we can create, your book talks about a resource allocation graph. Okay? But I want to put this in terms of resource allocation matrices. So this is one place where the way I explain it in class is diverging from the way that the book explains it. Okay? I'm hopeful that having 2 different explanations of the same concept will be a benefit to you instead of a hindrance. You can let me know. Okay? So what does that look like? What does a resource allocation matrix look like? Well, it looks something like this. Scroll down here. So let's talk about what we're seeing here. We have A, B, C, D, and E. Right? There's 5 processes. Each one of those is a process. And we've got 1, 2, 3, 4 tape drives. And this is just an example. Tape drives, plotters, printers, CD-ROMs. 4 resources. Okay? This matrix tells us what resources are assigned. How many resources of each type are assigned to each process. Okay? They've got, so for example, process A has 3 tape drives, 0 plotters, 1 printer, and 1 CD-ROM. Okay? This matrix tells us the number of resources that A might still need at a maximum. Okay? So for each of these, each of these resources, the process has told us ahead of time what their maximum claim is. And we know that the maximum claim of A on tape drives is 4. They currently have 3. They might need 1 more. Okay? And we know that on plotters, it's 1. They currently have 0. They might need 1 more. They currently have 1 printer. That's the maximum claim they have on printers. And they currently have 1 CD-ROM. That's the maximum claim on CD-ROMs. And we know that for both of those tables because we know each combination of process and resource. Okay? So if you look at a position in this grid, you're going to find the process's maximum still possible needed requests for printers. Now, it's not that they're going to request them all at the same time necessarily, right? They may never maximize out. But the worst case would be if they all maximized at the same time. Okay? So it's sufficient to assume that they do all maximize at the same time to find out if there's a possibility of a deadlock. And if there is not the possibility of a deadlock in this system, then what kind of state are we in? A safe state. Okay, we're in a safe state if that's the case. All right, so Dexter says, let's assume the worst. Assume the worst with this. All right, so what's over here? This is the existence vector. So E is, so this is the total number of resources of tape drives, total number of tape drives in the system, the total number of plotters, the total number of printers, the total number of CD-ROMs. This is the possessed vector. We can actually build this one because this is 3 plus 1 plus 1 is 5, and 1 plus 1 plus 1 is 3, and 1 plus 1 is, 2, and 1 plus 1 is 2. So that's the number that are currently possessed. And since we know each of these things, we also know how many are allocatable of each type. Okay? So let's assume that all the processes are going to immediately ask for their maximum resource allocation, okay, from this state, because this is the current state of the system. Is this a safe state? So let's assume they ask for it. So the banker's algorithm says, look for a row in the right. This is R. This is the resource assigned. Look for a row in the left. I don't know why this is called R in these slides. I should have gone in and changed it, but this is R and this is A. Resources owned and resources asked for. I don't know. I'm making it up. Okay, but that's the idea. So look for a row in this matrix. Okay, whose unmet resource needs are all smaller than or equal to over here, or rather here, A. Okay? In other words, can I find a process where I have enough unclaimed resources that I can fill in this guy? Okay? A currently has 3, 1, and 1. Can I give it 1, 1, 0, 0? I can give it 1, but I don't have another plotter to give it right now. Okay? And so it doesn't matter that that's not asking for anything else. It's blocking on a plotter. Okay? So I can't get rid of that yet. But here's B. It has 0, 1, 0, 0. Can I give it 0, 1, 1, 2? Nope. Here's C. Can I give it 3, 1, 0, 0? Nope. Here's D. Can I give it 0, 0, 1, 0? Yeah, absolutely. I absolutely can. So let's go ahead and do that. Let it finish. And then it gives us back 1, 1, 0, 1. And we add that to A. Okay? So the new value of A after D finishes, the new A is 2, 1, 0, 2, 1. 2, 1, 2, 1. Okay? Does that make sense? How I got that? Okay? So now I continue in this loop. Can I give E 2, 1, 1, 0? Yes, because I currently have 2, 1, 2, 1. And so E can finish. And so it's going to give us back nothing. Oh, well, right? But D and E are finished now. Okay? Dive back in. Can I give A 1, 1, 0, 0? Process A 1, 1, 0, 0. Yeah, because I have 2, 1, 2, 1. But all of those numbers individually are bigger. Okay? So A is going to give back 3, 1, 1, 3, 0, 1, 1. And that's going to give us 5, 1, 3, 1. Can I give B 0, 1, 1, 2? Yeah, because I've got 5, 1, 3, 1 currently. So I can do that. I'll give B 0, 1, 1, 2. It finishes, and it gives us back an additional 0, 1, 0, 0 for 5, 2, 3, 1. Okay. 5, 2, 3, 1. And so where was I? Can I give C 3, 1, 0, 0? Yep, I can, because I've got 5, 2, 3, 1. So is this deadlocked? Nope, because we eliminated all the processes. Okay. In fact, not only is it not deadlocked, not only have we determined that this is not deadlocked, but we have determined that this whole thing is a safe state and cannot become deadlocked. Okay? So the act of avoidance then, the way we avoid is we do not let requests come in unless we can prove that the additional requests don't move us out of a safe state. Okay, in the worst case. Right? And we do that by using the banker's algorithm. Is this the panacea that it appears to be? Is this reasonable? Is it going to work? What's the first assumption I told you to make? What's the first thing that had to happen? When we started talking about Dijkstra's banker's algorithm. It is the worst case, but back up a little bit further. Back the tape up in your head a little bit further. Is that reasonable? Right? A process, every process needs to know the maximum resource it's going to ask for. That's a hard ask. You know, it's difficult. Think of yourself. Think of what the programs you write. You don't think about what's the maximum number of resources I'm going to ask for when I write this program, right? And how would you even? How could a system exist that even would poll processes so that they could say how many resources they're going to potentially ask for? Okay. This falls under more theoretical than anything else. Okay. Now there are some practical applications, but they are estimates. They're based on estimates, the best estimate we can give of the maximum value, the maximum number of resources that a process might want. Okay. The other thing to consider is that this assumes that this is that we have a static set of processes, and the fact that processes are coming and going all the time complicates this more than it seems like it currently works. Okay, it's not a panacea, like I said, but you know, it's an interesting theoretical approach. Okay. I like Dijkstra just as much as the next person. It doesn't work in the real world. Okay. All right, let's stop there. Not only are we out of time, but that's also where we stopped on Tuesday. We will finish talking about deadlocks with a brief segment on deadlock prevention on next week.
We have an exercise for size.
Yes.
What is focus on? Which chapter?
It's on deadlocks. Yeah. So it's chapter 5. Yeah. So not only is your reading for chapter 5, but by I think I said next Friday, exercise number 5 is due. So you should also be working on that. That came out this afternoon. Okay. All right. I'll see you guys next week.